Now I will work on an example. This is going to be mostly based on the material balance. The example is about a draining tank. We are going to make the analysis on a tank that is draining through an orifice. Orifice is an opening in the tank, and this orifice releases the fluid based on the head pressure. All right, the head pressure is the external pressure plus the pressure at the point of orifice imposed by the static head, static pressure. So here, this is our external pressure. At this point, the pressure should be equal to external pressure plus rho, the density of the liquid here, the gravitational acceleration constant, times the liquid head. Well, the tank drains and the liquid head changes. This height is a function of time. All right? That makes this pressure a function of time. That makes the flow rate a function of time. Right? Now let's see how we are going to resolve this problem. Conservation of mass prevails. dm over dt is equal to m dot of t, and this m is already a function of t, and we are in a situation where we have three different variables: time, mass flow rate, and total mass. That is at any time inside the system. How are we going to solve this problem? We have only one equation. Now, through the use of characterizing dependent variables, perhaps we can find a common variable that connects everything together, and we can have one equation with one unknown. Let's see. Now, m dot of t is a function of the pressure. Now, this is a concept that we give you the details in the course of fluid mechanics. At this point, you have to take my word for it that this flow rate here is going to depend on the liquid height. Now, what I will do, I will just make an assumption. I will say that this m dot of t is a constant a, an arbitrary constant, times liquid height raised to a constant b. So I invented an expression. This expression satisfies the conditions that when height is equal to 0, the flow rate will be 0, and there is a perhaps nonlinear relationship between the height, liquid head, and the volumetric flow rate or mass flow rate. Okay? So, now this is one relationship that I have. This is A times h to the power b. I don't know A, I don't know B, but I still insist that I can solve this problem. Now, can I write m in terms of h? Well, yes. Mass in the tank is the cross-sectional area times h, this is the volume in the tank, times the liquid density. Okay? Density is constant, this is liquid. Area is constant, it's cylindric. Now, dm over dt then, a times rho times dh over dt. On the other side, I have lowercase a, it's a proportionality constant, h to the power b, power I don't know. But you see, my equation with mass that has turned into an equation of height. Now what did I do? I used a characterizing dependent variable, which is the height, to represent both mass in its functionality and m dot in its functionality. Okay? So h is a characterizing dependent variable, while mass is the fundamental dependent variable. So what makes it fundamental? For fundamental dependent variables, we write conservation laws. Fundamental dependent variable of mass, conservation of mass. Fundamental dependent variable of energy, conservation of energy. But then we can convert mass into a function of height, area, and density. Mass flow rate into a function of proportionality constants and height, and so on and so forth. All right? Characterizing. Okay. So now let's take this portion of this equation. And of course, we need an initial variable. This is a first order differential equation. I need an initial variable. One initial variable. So at time t is equal to 0, h was equal to h0. Okay? So I will integrate dh over h to the power b is equal to a over capital A times rho times dt from 0 to t, from h0 to h. Okay? This side is easy. A, t, and so on and so forth. So I'm going to carry out an integration slowly but surely. H to the power minus b dh integral is equal to, I'm going to increase the order by 1 and divide it by that. So this is 1 over 1 minus b times h to the power 1 minus b between h0 and h. That is equal to 1 over 1 minus b h to the power 1 minus b minus h0 to the power 1 minus b. That is equal to a divided by a sub c. Let's call this a sub c so that it is cross-sectional area times, I had something, right? Density times t. Now I have a relationship between height and time. What I can do is to go to the laboratory, make a measurement, and perhaps that measurement can give me a relationship. Now I have the equation. I will rearrange this equation, right? I will rearrange this equation for h of t. I hope that you can see this part is equal to 1 minus b goes to the other side. 1 minus b times a divided by a sub c times rho times t plus H0, 1 minus B. I have to take it into the square brackets, and this is 1 over 1 minus B. All right? So, or I can generate an equation for t as a function of h, which is not as meaningful as this. So just make a measurement of time, h of t, collect the data, and make this measurement. Just in your own homes, you can make this measurement. You can just take a plastic bottle, you can poke a hole into the bottom of that plastic bottle. All right, so take a plastic bottle. I'm sure you have plenty at your disposal, having different sizes. Just take a small one, take a large one. Use a ruler. Use the video capabilities of your smartphones and record the position, liquid level, and the time, right? Now I have an equation that reflects height as a function of time. Now you're going to use the data to obtain A's and B's, all right? So my challenge is onto you that you need to do certain manipulations of the data. You may have to represent your diagram, graph in different coordinates, obtain A and B from the data that you would obtain at the convenience of your home in your kitchen using a simple plastic bottle with a poked hole. Now you can change the size of the hole and repeat the measurement, but my recommendation is not to rely on one single measurement. Make your measurements a couple of times, 2 or 3 times, and make sure that you are protecting yourself from the random errors that can occur during making such measurements. So the result will teach you few things about experimentation, few things about how this order allow us to relate a mass flow rate to the height. And of course, for those of you who are curious, you can find out about the orifice equation. I write orifice equation, all right? The technical information infrastructure is at your fingertips. You can do an internet search and find out about the orifice equation, and you can compare your estimations with what we have in the literature. So this is the draining tank problem. I attempted this problem only through the material balance. I made an assumption. I converted an equation of the fundamental variable of mass to a characterizing variable of height through the relationships, just like I did for temperature energy conversions. And as a result, now I have an equation that represents height as a function of time, which will give me the mass flow rate as a function of time, right? Knowing this helps me design systems in a way that I know how long it will take to drain this tank. And certain times, precise information is very, very important.